Hi everyone, so this is going to be the second pre-lecture video for PCS 622. I'm going to go over a little bit of theory here on calculating Fourier coefficients. So before you're watching this, I hope that you're familiar with the following two things. I hope you understand at least a little bit the idea of a Fourier series. So the idea is you're taking some function f of x, which is periodic, and it has a period of 2 pi, and you're writing it as a combination of sines and cosines and an additional constant term here. So there's this constant term, and then there's an infinite sum of sines and cosines with different weights. So you're figuring out how to represent this periodic function f in terms of as a combination of sines and cosines, and the particular combination of sines and cosines are these ans and bns. These are numbers called the Fourier coefficients. So I'm hoping you're familiar with that formula at least. And then the second thing I hope you're familiar with is the orthogonality of sine and cosine functions. So it turns out that you can show this, and that if you multiply two cosine functions together and integrate from minus pi to pi, the answer is 0 unless they're the exact same cosine. So if this number n is the same as this number m, then the answer will be pi. If n is different than m, the answer will be 0. Same is true of sine functions. So it's 0 if the m and n are not the same, and it's equal to pi if m is equal to n. And if you mix them, if you mix up a sine and a cosine, then n and m, the answer is always 0 no matter what n and m are. So those are the things that we're going to use going forward. So I hope that you're familiar with those concepts. Okay, so let's get into it a little bit here. Okay, so the idea here, the main purpose of this little mini lecture is our goal is to calculate these Fourier coefficients. So a goal here is to calculate an, a0, an, and bn if the function f of x is known. Okay, so suppose you know the function f of x, and you want to know exactly what is the combination of sines and cosines that I can use to get f of x. So in other words, I know this function f of x here, and I want to determine these coefficients, an, bn, a0 over 2. Okay. This should remind you a bit of the Taylor series. So let me just put here a side note. The Taylor series, remember, it's a different series. So the Taylor series looked something like this, right? F of x was equal to some sum over n times some coefficients, maybe I call them Cn, x minus x0 to the power n. N equals, 0 to infinity, let's say. So same kind of idea. It's like, suppose I know the function f of x and I want to know its Taylor series. I need to know how do I get those coefficients Cn. And we talked about it in the last video that the way to do it was to do something to both sides of this equation. And in this case it was take derivatives of both sides and plug in x0. Taking derivatives of both sides. And then plugging in x equals to x0 allowed us to isolate those coefficients Cn, and we got Cn was 1 over n factorial, the nth derivative of x evaluated at x0. So that's the kind of frame of reference, so that's a side note. Now, we have a different series here, so we're going to need to do some different operations to get the ans and bns listed up here. But the idea is the same. I need to do something to the left side and something to the right side, do something to both sides of this equation to isolate the ans and the bns. Okay, so that's what we're going to do. All right, so let me just rewrite the Fourier series, and I'm going to write it out in kind of more just explicitly, just so it's a little bit more transparent what's going on. Okay, so what I've written here is the first few terms of the Fourier series of f of x. Okay, so here's the function f, and we're saying we know that function. And then it's written as a sum of sines and cosines, and I just wrote down the first few terms. So there's this constant term, and then there's a1 cosine of x, this is n equals to 1, a2 cosine of 2x, that's n equals 2, a3 cosine 3x, n equals 3, and then I wrote down some b terms with the sign, right, b1, b2, b3. And of course, this is an infinite series, so there's an infinite number of extra terms which I'm not writing down, but hopefully you get the idea from just these few. Okay, so now the question for you is, what can I do to both sides of this equation? So I need to do something to the left side and something to the right side in order to get, let's just try to isolate this one a0. I want to somehow get a0 over 2. Sometimes when I do this, students say, well, just move all this stuff to the other side, but that's not helpful, right? Because I don't know these things. I don't know a1, a2, a3, or b1, b2, b3. I want to try to determine those. I don't know them. I need to get rid of all of the other a's and b's and isolate only a0. So I want a0 in terms of f of x only. All right, let me give you a second. Maybe it's good for you to pause the video and see if you can come up with some operation to do on both sides. So maybe you've paused the video and thought about it. In the Taylor series, we took derivatives. But in this case, we need to do something different. We need to do actually an integral. So think about, let's do the following thing. Let's integrate both sides. From minus pi to pi. So I'm going to slap integral signs in front of every term here. So maybe I'll use a different color. Integrate this side from minus pi to pi dx. And I have to do that to every single term here, minus pi to pi dx. The integral is a linear operation, so the integral of the sum is the sum of the integrals, right? That's why I can write the integral of each term. And let's just do every single one of those. Minus pi to pi dx, 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 and one more, minus pi to pi dx. Okay. Now, that looks like it made everything more complicated, right? But my claim is actually it made it more simple. Why did it make it simple? Remember, a cosine is an oscillating function. Half the time it's positive, half the time it's negative, right? Over a period. And the integration range minus pi to pi is over a full period of a cosine and also of a sine here, right? So the integration range is over a full period. What about this one? These two? Well, those have a period of even shorter period, right? The period of cosine 2x is pi, and the period of sine 2x is pi. So if I integrate over a range minus pi to pi, I'm integrating over 2 periods, right? And these ones here, I'm integrating over 3 periods. And the next term would be over 4 periods. And if I was integrating just a single trig function over a period, or 2 periods, or 3 periods, or 4 periods, the answer is going to be 0, right? So the claim is that all of these are 0. All of these terms, this is 0, this is 0, because I'm integrating a single trig function which oscillates, half the time it's positive, half the time it's negative, over a full period, and the answer will be 0. If you don't believe me, I invite you to try it out yourself, so let me give that to you as an exercise. Do it by hand. Go minus pi to pi, cosine of nx, let n be any number, dx. Just do the integral using your usual techniques that you learned in calc class, and show that it's equal to 0. Okay. And the same is true for sine. So convince yourself that all of those terms are 0. So you see what I did. by multiplying by the, or not by multiplying, but by doing the integral of both sides, I got rid of all the terms except for one. Okay, so now I have this much simpler equation to deal with, which looks like this. Integral minus pi to pi, f of x dx, is equal to integral minus pi to pi, a0 over 2 dx, plus everything else is 0. And this integral is simple, the one on the left side. It's a0 over 2 because a0 is a constant, integral minus pi to pi dx, which is a0 over 2 times 2 pi, which is equal to a0 times pi. Solving for a0, what I've determined is a0 is equal to 1 over pi, integral minus pi to pi, f of x dx. So remember, what were we trying to do? We were trying to determine these coefficients, a0, a1, a2, a3, if I know the function f of x. So we've done one coefficient. The bad news is we have an infinite number more to do, but you'll see that the other ones will come more quickly. We don't have to do them all one at a time. But you can see the idea, right? If I know this function f of x, and I want to know this coefficient a0, I just do this integral from minus pi to pi of the function f of x and divide by pi. By the way, it's worth mentioning what is the meaning of this. You might remember that the average value of a function, I don't know, maybe you learned this in your calculus class. The average value of a function over some integral, let's say a to b, is 1 over b minus a times f of x dx. So what it tells you is that a0 is equal to, maybe I'll write it in words here, a0 over 2 is equal to the average value of the function on the interval minus pi to pi. Okay, so that's the meaning of this coefficient a0. It's related to the average value. There's one little tricky bit, which is you have to remember this factor of 2 there. But a0 over 2 is the average value of f. Okay, that's the physical meaning of this quantity a0. Okay, so we've done the first coefficient. We figured out if I know f, I can figure out what a0 is. Now we need the other ones, a1, a2, a3. So let's think about how to go forward with that. I'll start by writing again the Fourier series. Okay, so now our goal is to figure out how can I get these other coefficients, a1, a2, a3, b1, b2, b3, and so on. There's an infinite number of those. So to maybe focus on a concrete example, let's say, suppose I want to find b2. That's the coefficient of the thing in, that's the thing in front of the sine 2x term in the Fourier series. Same idea, I need to do something to the left side and the same thing to the right side in order to get rid of everything else and isolate b2. So, a little bit harder now. Maybe you can take a moment to pause the video and think about, can you determine what you should do? Sorry, I forgot a plus sign here. To both sides. And I'll give you a hint. You need to go back up and use, remember the things that I mentioned that you should be familiar with, is the orthogonality. So we're going to use this orthogonality here in order to isolate the thing that we want. Notice that these integrals of sines and cosine, two products of cosines and sines of sine and cosine, are 0 except for under very special circumstances, m equals to n. So let me give you that hint about thinking about the orthogonality. Can you pause the video and think about what you can do to both sides to isolate just this term, b2 here? Okay, so if you're thinking that has to do with an integral, you're right, but you can't just integrate both sides because we pulled that trick up here, right? We integrated both sides and we got a0. So I have to do something else. And the trick is, if I want b2, what I'm going to do is multiply both sides by sine of 2x. Okay, so let me do that. I'll pause the video and just multiply everything by sine 2x. So there it is. I multiplied both sides by sine 2x, so I get a sine 2x in every term. Now the thing looks more complicated, but if you're thinking about the orthogonality now, the integrals of most of these terms are zeros. So now I'm going to integrate both sides. Both sides, same as before, from minus pi to pi. So let me do that. Okay, so there we go. Now it looks a bit more complicated. But just like before, it turns out that most of these terms are going to be 0. So let's look at this first one here. This term here. This is a constant, so it comes outside the integral, so that we don't need to worry about. And then it's an integral of a single trig function over a multiple of the period, right? Sine 2x has a period of pi. This is an integral over 2 periods. And so an integral of a single trig function from minus pi to pi is going to be 0. So this is 0 because it's a single trig function over 2 periods, right? So that's 0. How about the second term here? Integral cosine x sine 2x. That's 0 because, remember, whenever I have an integral of a cosine and a sine, it's going to be 0 by orthogonality. So this is 0 by orthogonality. I'm using, if I go up, I'm using these relationships, right? The integral of a sine times a cosine from minus pi to pi is equal to 0, no matter what the sine or the cosine is inside the sine and the cosine, right? Same thing here. This is 0. Sorry, this is 0. Same thing here. This is 0. That one is 0 because, if I go back up to the orthogonality relationship, that's a sine times a sine. But with m not equal to n, right? In one of those, m is equal to 1, and the other one, n is equal to 2, right? So the thing inside of the sine and the two sines, so the sine of x, sine of 2x, this is orthogonality with m not equal to n. So that's 0. This one is the only one that's not 0. This is not 0, right? So all the others were 0. And there's a bunch of other terms which I didn't write, you know, for example, cosine 3x, cosine 4x, cosine 5x, sine 3x, sine 4x, sine 5x. All of those, when I multiply by sine 2x and integrate, everything will be 0. So this is the only non-zero term. And we know the value of that integral, so maybe I'll just do it very slowly first time through. So now we have this equation, minus pi to pi, f of x sine of 2x dx is equal to, let me bring the b2 out front, minus pi to pi, sine of 2x sine of 2x dx. And this integral is equal to pi. Remember, if the two things have the same argument, so if m is equal to n, the integral is equal to pi. And if m is not equal to n, the integral is equal to 0. So what I found, solving now for b2, 1 over pi, divide by the pi, integral minus pi to pi, f of x, sine of 2x, dx. So again, if I know the function f of x, and I want to calculate this second Fourier coefficient b2, what I should do is multiply the function by sine 2x, and then integrate from minus pi to pi, do the integral, and that will tell me this number b2. Okay. Now you're wondering, well, what about b3 and what about a3? So hopefully you get the idea for how to do the others. So for example, what if I wanted a3? Then I would multiply by cosine of 3x and do the integral. Okay. And what if I wanted b1? I would multiply by sine of x and do the integral. Okay, so if you're having trouble, maybe it's an exercise for you. So an exercise for you would be to maybe try another one. Determine the formula for, let's say, A5. Well, 5 is, let's try A4. And try to go through the same steps that I did above. You have to think about, what do I have to do to both sides to isolate just the A4 term? It might help you to try that out. But I'm not going to go through every single coefficient, so now the last thing I'm going to do is, let's do it in general. Okay, so let me try to determine the general formula for an and bn for any value of n. And you can probably guess what it is just by looking at this, but let's prove it. Okay, so let's try to just generalize it by doing a bit of, with a bit more fancy notation. Suppose I want to know the coefficient am. So m is any number, all right? So I'm just leaving m arbitrary. M could be 1, 2, 3, 4, 5, any positive integer, okay? But I'm going to leave it as m, so you can use the formula for any integer. What should I do to both sides? Hopefully by the previous example you have the idea of what I should do is multiply both sides. Sorry, going a little bit too fast. So this is the Fourier series, right, for f. I just wrote the Fourier series with the sums in there. And I broke the sums into two pieces, so there's a sum with cosines and a sum with sines just to save myself, or just to give myself some extra space. Okay, so there's the constant term here, and then there's the adding up all the combinations of the cosines and the combinations of the sines. All right, multiply both sides by cosine of mx, okay? So let's multiply both sides by cosine of mx. Remember, m is this value here, so m is a fixed value. It's different than n. N is summed over, right? So n changes value depending on which term I am in the sum. M is a fixed value, so I'm multiplying this by cosine of mx, and multiply this by cosine of mx, and multiply this by cosine of mx. Okay? So, very important. It's very easy to get confused, right? N is a summed variable. So it has a different value depending on which term you're in the sum, right? The first term has n equal 1, the second term has n equal 2, the third term has n equal 3. M is just some fixed value the whole time. So n has a different value for each term. And m is fixed. So it's the same everywhere. I mean, it's not summed over. You can see that the n is summed over, right? It's in the bottom of that sum, but m is just a fixed number. Okay, now what do? Now put some integral signs. Integrate both sides from minus pi to pi. Minus pi to pi. Minus pi to pi. Minus pi to pi. dx, right? I should always put the dx. 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 Okay, now it looks kind of complicated. But it's not so bad. Okay, let's assume that m is equal to, I think I said any positive integer, right? So m is not 0. So if m is not 0, this first term is 0, because it's an integral of a single trig function, right? Over a period. So that's 0. Now let's think about these terms here. First thing I'm going to do is I'm going to interchange the sums and the integrals, all right? The integral of the sum is equal to the sum of the integrals. So let me interchange the sum and the integrals, and I will rewrite this whole thing. Okay, so I just rewrote the equation above. I made it into a single sum because, those two sums are over the same, they both go from n equals 1 to infinity, so I can just write it as a single sum. And then I'm summing up all of these integrals, okay, minus pi to pi. And you can see how this is going to work now. This one, remember, sine nx cosine mx from minus pi to pi, this is equal to 0 by orthogonality. It doesn't matter what n and m are. This second one, the first one there, let's think about what this means. So I've got here a bunch of integrals, right? N equals 1 to infinity. Integral minus pi to pi. I can pull the an outside of the integral because it's just a constant. Minus pi to pi. Cosine of nx, cosine of mx. Now remember, m is fixed, right? M is like 1 or 2 or 3. M is a fixed number. There's an infinite number of integrals here, because they're all being summed over for every value of n. So the first term has cosine x times cosine mx. The second term has cosine 2x times cosine mx. The third term has cosine 3x times cosine mx. But you know, all of those integrals except for one are going to be 0. So these are all 0 except there's one term. The term when n, the summed variable, is equal to m. Okay, so remember, if you start writing this out, there's an infinite number of terms there, but there's only one of those terms when the summed variable n matches the fixed variable m. Okay, so out of all of those infinite number of terms, only one of them is non-zero, and so I can ignore all the other ones. So finally what I have here is minus pi to pi f of x cosine of mx dx is equal to, there's only one term when n is equal to m, so I'm going to have here am, right? Out of all the n's, there's only one where that n matches the m on the left-hand side. Okay, so I'm only writing that single term, am, integral minus pi to pi, cosine, again, now the n matches the m, mx, cosine mx dx. And this integral we know is equal to pi, am times pi. So what we got out of this is that m is any value, any integer, divide by the pi, 1 over pi, integral minus pi to pi, f of x, cosine of mx dx. So if I want to know a1, then I multiply by cosine of 1 times x and do this integral. If I want to know a3, then m is equal to 3. I multiply by cosine 3x and do the integral. Okay, so this works for any value of n. Sorry, for any value of m. And actually, it works even for m equals to 0 because we found, if I go back up here, a0, where is it, way up here, was 1 over pi without any cosine at all, right? So it also works for m equals to 0 because if m is equal to 0, I get the formula we got before. So m here is equal to 0, 1, 2, 3, any positive integer. Okay. How do I get the b's? bm. Hopefully it's not too hard to see. You go through those same steps, minus pi to pi, f of x, sine of mx dx. Here m is equal to 1, 2, 3, so on. There's no b0 term if you go back up and look at the Fourier series. So let's go back up and look at the Fourier series all the way to the top here, right? There's an a0 term, which is a constant term. And then there's A1, A2, A3, and B1, B2, B3, but there's no B0 term. So what we have now is this was our main goal, right? If I know a function f of x, which is periodic and it has a period of 2 pi, and I want to write the Fourier series of that function, to get the Fourier coefficients am and bm, I take the function, I multiply by what the particular value of cosine and sine. If I want am, I multiply by cosine. If I want bm, I multiply by sine. And then I do this integral, and that will tell me the Fourier coefficients. Okay, so this formula is quite important, or these formulas are quite important. And we will do some examples of calculating Fourier coefficients in class, but at least we've derived the main formulas for how to do that.